Okay, this video is to serve as a quick review of angular momentum. So angular momentum, we look at it just like linear momentum from two perspectives. One, looking at if we have an external torque or force acting on a system, then we have a change in angular momentum. Or if we have an isolated system where there are no external torques or forces, then we know that the change in the momentum will be equal to zero. So total momentum before equals the total momentum after, just like linear momentum. So angular momentum, as we figured out, has a capital letter L is what we use to symbolize it. It has direction, it's a vector. It follows the right-hand rule, so we can go through that real quick since I have a video working. So if we have a circle that is moving with some angular velocity, you take your right hand, your fingers follow the direction of the rotation, stick your thumb out, and your thumb points the direction of the angular momentum. So in this case, it would be directed outward. Similarly, if we had a thing that was rotating and was going the other way, now, harder to do, fingers follow the direction of rotation, now my thumb is pointing into the page. So that's how we determine the direction of angular momentum. Okay, the formula for angular momentum is actually a cross product between the radial vector, which is the distance, the radial position vector from the center of the rotation or the pivot point, crossed with the linear momentum. So if we were to look at an object that's moving in a circle, okay, mass m, that has some linear velocity and linear momentum as it moves about a circle relative to this observation point. The radial distance would be the distance from the pivot point to where it's moving. That would be our R value. Now, interestingly enough, if a particle is not moving in a circle, if it's moving in a straight line, it also has angular momentum relative to an observation point. So what do I mean? We take a point here, let's say we have a couple of different objects here, M1, M2, and M3, and they are all moving with some velocity upwards. Let's just say it's all the same velocity, and they're all just moving along in this straight line. Well, all of these particles will have angular momentum relative to this observation point. So if we look at the distance from the observation points, we'll call this one R1, this one R2, and we'll call this distance R3. So that's from the pivot point to the object. But if we recall, this is a cross product, so our angular momentum is actually equal to the perpendicular component of that radial vector times the linear momentum. So for all three of these objects, they all have angular momentum relative to this pivot point, but this is representing our perpendicular. So how do we figure out the R perpendicular? Just like we did with torques, we extend the direction of the velocity vector here, and then we drop a perpendicular. So the angular momentum of this object here would be R2 times M1 times its velocity. This angular momentum would be R2 times M2 times its velocity, and this one would be R2 times M3 times the velocity. So you could calculate the angular momentum of a particle moving in a straight line relative to the origin. So that one is our first representation of that. Let's look at some other ideas of objects moving in a straight line. So again, we have a observation point, and let's say we have a particle here that is moving with velocity and momentum. But here, this velocity vector passes through the observation point or the pivot point. In this case, our perpendicular component of the radial arm would be equal to 0. So this would have no angular momentum if the motion passes through that pivot point. Much like there's no torque exerted if the lever arm passes through the pivot point. Okay. Last example is if it's just moving at some random angle. So again, we have an observation point, we have some mass m, and let's say it has some velocity in that direction. If we want to calculate the angular momentum, we want to take the perpendicular component of the radial arm times the linear momentum. And to do that, we extend kind of the direction that it's moving, we drop the perpendicular, and that would be our R perpendicular. And again, you'd have to know some angle relative to something in order to determine that R perpendicular if you were given the distance from here. So If you knew this distance right here and you had that angle, that would be the sine of the angle. So if this was theta and that was given, it would be r sine theta times the linear momentum. So those are the different instances of looking at a particle moving in a straight line as well as a particle moving in a circle. So there's one more way that we can calculate the angular momentum of a system, and that's if we look at its rotational inertia times its angular velocity. This is a complete analog to looking at linear momentum as mass times velocity. Mass and inertia are analogs of each other, and v and omega are also analogs to each other. In fact, if we look at the rotational inertia of a particle, we know it's equal to mr squared. If I plug that in over there and use our non-slip condition, which is v over r, we get L equals mr squared v over r. R's cancel out, and you'll end up with the m times r times v, which is what we started with in the beginning. So they're equivalent equations, it's just how you want to deal with it. So let's look at examples of an extended rigid body. Let's say we have a solid disk here that is rotating with some angular velocity omega. Well, the angular momentum of that would just be its rotational inertia times the angular speed. And for a solid disk, it would be 1/2 mr squared. The omega, you could use that non-slip condition. You could cancel out one of the r's. So again, you can kind of use some of the cancellation or some of the things that we know to simplify it depending on what you need to solve for. So that's solid disk, and of course it would apply to rolling spheres and hoops and all that kind of stuff. So let's look at something a little bit more complicated. Let's say we have a solid disk. So we got a disk here, and it has a mass called big M times d, and it has a radius r. So this is the information about the disk. And let's say we have a person standing on the disk right here, and they have mass m, and let's say that they are a distance little r away, and we can treat this person as a particle. Nice to be simplified that way. And let's say this thing is rotating with some angular velocity, and we wanted to determine the total angular momentum. Well, the total angular momentum is just going to be the rotational inertia of the disk plus the rotational inertia of the particle. That will give us our total rotational inertia times the angular velocity of the system. In this case, both things are moving with the same angular velocity, so that part can get factored out. So just kind of adding a little bit of the information. The disk will be 1/2 mass of the disk times its radius squared, plus the rotational inertia of the particle will be little m times little r squared times omega, and we can solve for the total angular momentum of something that's rotating. So, and you can do this, you know, with all kinds of systems. If you had like a rod system that's pivoting, and again, I will give you the value for the rotational inertia of your system. You could have particles hanging off here and have this whole thing rotating, and you could determine your angular momentum by just looking at the total rotational inertia times the angular velocity of the system. So let's just do one quick problem, just maybe using a few numbers. Let's go back to looking at particles. So let's say we have an axis of rotation here, and let's have a particle that's like 2r away, and let's say it has a mass of 2m, and let's say it's moving in a clockwise direction, so that would give it a negative angular velocity. And let's say we have another particle on some thin rod here, and it has a radial distance of r0 and a mass of just m, and let's say that its angular velocity is positive or counterclockwise, and these two are equal in magnitude. So I want to determine the total angular momentum of my system. Well, that's just going to be equal to the, let's call this one particle 1, and this guy over here particle 2. I take the rotational inertia of particle 1 times its angular velocity plus the rotational inertia of particle 2 times its angular velocity. And I said that they were equal but opposite in magnitude, so we have to make sure that we take care of that in the sign. So particle would just be m r0 squared would be rotational inertia times omega. And then over here, we would add, but actually this is going to make us subtract it, but I'll put that in a little bit later. Twice the mass times 2 r naught squared times minus omega. So simplifying a few variables here, you get m r naught squared times omega, plus this 2 squared is 4 times 2 is 8, m r naught squared, and then we'll have a minus omega, and I'll put that minus sign out front. So adding them together, I get minus 7 m r naught squared times omega. So we can just take it through the steps to calculate the total angular momentum of a system. Okay, next video will be on conservation of angular momentum.